All right, guys, we got a slightly more complicated system we also need to talk about, which is the eye. And the eye is a little bit more complicated because it has an aperture, which is like the shutter or on the camera, but it's a multi-lens system, and it also has the retina, which acts like the film on a camera. So if I think about the eye from front to back, I have things like the pupil, the cornea. We have the crystalline lens and the retina. And we have to consider what each one of these things does. So what the pupil does is it changes in shape, allowing more or less light in. And in a dark room, you'll see that your pupils get large to allow more light in, so we can create that image on our retina and see what we see. And then in bright sun, you'd see that it gets much smaller. And in that case, we are using less light, or we need less light, and we are allowing less light in. The cornea is a fixed lens in the front of our eye that begins focusing the light from an image in the room onto the back of our retina. But as we hopefully know, when I'm in a room, right, I can focus on things in the foreground and the middle ground and in the background. So I can change the focal length of my eye. So that means I have more than one lens in place, and that second lens is the crystalline lens. It allows me to change my focal length. So most of the bending actually does occur at the cornea, and that's because the index of refraction change is the largest, and by Snell's law that means the change in the angle of the light's the biggest, because the N of air is about 1 and the N inside our eye is about that of water, so it's about 1.3. As I get to the crystalline lens, I actually change the index of refraction, the power of the lens, and it's sort of a very complicated structure where light's bent a little bit and a little bit more and a little bit more and a little bit more, but we're just going to think of it as the piece of the eye that allows us to change our focal point of our eye and gives us information about the near point and the far point. So as we get older, our ability to focus light sort of changes, and that has to do with the rigidity of the crystalline lens, because the crystalline lens has a totally relaxed state, which bends the light the least, and a contracted state, which bends the light the most. And as we get older, our contracted state doesn't bend light as well. So when we're very young, the near point that we have might be something along the lines of 7 centimeters. And the far point is going to change over our lifetime and might end up at something like 200 centimeters. The far point is our relaxed crystalline lens, and that tends to stay about the same, and that should be somewhere out at about 5 meters or 2 meters, a few meters. And this gives us our nearsightedness and our farsightedness, and allows us to sort of understand what's going on there and how we can use corrective lenses to fix this issue. The last piece here is the retina, and it's like the film. So here our image is focused, and that image is transmitted to electrical pulses, which our brain then reads. And it actually is an inverted image that our mind then, or not our mind, but our brain flips right side up. So how is it that this system fails us? Well, one of the ways it fails us is if I've got an object over here, and I've got my eye, and here's my retina, I might not bend the light so that it hits where it's supposed to. So instead of focusing the light on, say, the retina itself, I could focus the light a little bit in front of the retina or a little bit behind the retina. And this creates nearsightedness and farsightedness. So if the light is focused in front of the retina, then I end up with blurry images. And what I need is a secondary lens, like glasses in place, that can push that image back to the retina. So I need something that actually allows it to spread the light out. So in this case, I need to use a diverging lens. To correct my eyesight. On the other hand, if I focus the light too far back, I need to add some bending power. So in this case, what I need is a converging lens. To allow my image to be formed at the retina. And when that image, that light, reaches the retina, I have to think about what it is that's actually interpreting this light. And this area, the retina, acts like a CCD, like in a digital camera, and is sensed by cones and rods. And rods give us things like peripheral vision, dark vision, and those sorts of things, but aren't good at detail and aren't actually color sensing. And one optic nerve can have hundreds of rods on it. On the other hand, a cone needs more light, but allows us to have color vision and detailed vision, and one optic nerve works with one cone. So cones are sort of this detailed structure and more complicated system. And through our cones and rods, what happens then is the image that's focused on the back of our retina is transmitted into electrical impulses, and then our eye talks to our brain through these electrical impulses, and we see what we see. So just to review, our eye can really be thought of as these four pieces: the pupil, which determines how much light gets into our eye; the cornea, which does the initial fixed bending; the crystalline lens that allows us to change the focal length of our eye and be able to see things close to us and far away; and the retina, which is like the film or the CCD at the back of our eye that takes that image, turns it into electrical impulses and then sends that to our brain. The crystalline lens, in its flexibility, gives us our limiting near point and far points that give us nearsightedness and farsightedness. And when it's not good enough and we have eye problems and we need glasses, we have two different possible scenarios. One is our near point isn't sufficient, and one is our far point isn't sufficient. And this causes the images to either form in front of or behind the retina. And we can use a diverging lens to take that image that's in front of our retina and move it to our retina, or a converging lens to take the image that is behind our retina and move it to the retina. And that creates a three-lens system that allows us to see well, or as well as somebody with, say, 20/20 vision. Once I have that image at the retina, cones and rods interpret that image into electrical signals that are then sent to our brain. And it's these cones and rods that do things like give us peripheral vision, and color vision, and sort of the detail-oriented vision, with the rods being the peripheral vision and the low light vision, and the cones being the detailed vision and the color vision. So hopefully that sort of helps you understand what's going on when we think of the eye as an optical instrument.